In class today we talked about Ampere's law, but I'm going to go through it real quick. So what Ampere's law does is allows us to calculate magnetic field. For certain symmetries, and it's an easy way. Much easier. much easier than using the Biot-Savart law. So the first thing that we're going to look at before Ampere's law is Gauss's law for a magnetic field. And so what we would hope to do with Gauss's law for a magnetic field is look at the magnetic flux through any closed surface. So if we're going to look at this, we would construct our same cylinder, a Gaussian cylinder around this thing. But looking at the magnetic field from it, I guess we'll do that in red. The magnetic field would swirl, put our thumb in the direction of the current, our fingers swirl around it. The magnetic field would swirl around this thing like this. So I wouldn't actually see my magnetic field piercing through this. So in this case, Gauss's law for the magnetic field is 0. In all cases, Gauss's law for the magnetic field is 0. Because our enclosed sort of magnetic poles are always neutralized. They always go to 0 because there's no such thing as a monopole. We talked about that in class, just to review. Now, since we can't use Gauss's law, we're going to use Ampere's law. Ampere's law has to do with a line integral. So we have a closed loop, and it's the magnetic field. It's the line integral of the magnetic field with respect to that length. And that's going to be equal to mu0, or permittivity of free space, times the enclosed current. That's all there is to Ampere's law. Now looking at it again, we see our magnetic field looping around our cylinder like this. So if we were to have a front-on view of that, if the current's coming out at us, the magnetic field would be going around it like this, in concentric circles for different values of the magnetic field. So what we're going to do is take an Amperian loop and put it around our cylinder. It's not a great loop. So that loop is going to go around this cylinder. So the purple one will be for outside. That'll be for the radius of my loop, little r, is greater than the radius of the cylinder. That'll be one Amperian loop. And the other Amperian loop we do will be sort of inside, right here. Point P2, the brown one. So that will be for the radius of my loop is smaller than the radius of the cylinder. Now we'll look at the outside case first. It's the easiest one to deal with. So this dot product here, we want to have the magnetic field parallel to my loop. And we see with that swirling around, that's exactly what we get. We also want the magnetic field to be constant with respect to our integration. And if we look at that, it's the same distance away from everything, so it is. So here we have B dot dl equals mu0 times the enclosed current. Well, that comes out, and I have the line integral across my Amperian loop is equal to mu0 times the enclosed current, which is just I in this case. So as we take that line integral, it's 2 pi times the radius of my Amperian loop, and that's equal to mu0 times the enclosed current of I. So that magnetic field from a single wire on the outside comes out to be mu0 times I over 2 pi r. This is worth memorizing because it comes up a lot, but it's very, very easy to derive. This is how we get the magnetic field outside of any current-carrying wire, carrying current I. Now, inside of the loop gets a little bit more complicated. So we start off with Ampere's law, but it's this I enclosed thing that's going to be a little bit weird. Everything else is the same. My magnetic field here, it's still going to be swirling around there. It's still going to be constant at that radius. So that's still going to be B times 2 pi r. We have to figure out how to deal with mu 0 times I enclosed. Now if we look at this, we have current coming out, but at every point we have sort of a constant current coming out of this thing. And we've taken our Amperian loop and we've only enclosed some of our current. Now, so we have this new term. It's going to be J. It's current density, but it's current per unit of cross-sectional area. We're not necessarily going to use that here, but I enclosed for anything is going to be this J times the enclosed area. So our I enclosed here is equal to the total current I over the total area of my wire, pi big R squared, times my enclosed area, pi little r squared. Those pi's go away. So my I enclosed is I times r squared over big R squared. So B times 2 pi little r is equal to mu 0 times I r squared over big R squared. One of my r's goes away. And my magnetic field inside of this wire as a function of the radius is mu 0 I r over 2 pi times the radius of my wire squared. That's how we find the magnetic field inside of our wire. Now if we wanted to graph this, and I know you want to graph this, that's my magnetic field, and that's the radius of my wire. My magnetic field as a function of r gains linearly with r, and then once we're on the outside it decreases like 1 over r. That's the magnetic field inside and outside of the wire. Obviously the outside case is easy, and the inside case should remind us a little bit of what we did with Gauss's law. Ampere's law for a solenoid gets complicated. Since I can't draw a solenoid, this is what we have. Now a solenoid is nothing more than loops of wire. And we're going to use another new term. It's N, which is number of loops per meter. Number of loops per unit length. So we'll say that this particular one has N loops per unit length. Now looking at this, my current comes in, it goes around these loops, and this cutaway shows current coming out of the page on top and into the page on the bottom. So what we're going to do is use Ampere's law to look at point P1 and point P2, okay, and a certain degree of symmetry to do that. So at P1, or outside of our solenoid, we've got Ampere's law, B dot dl times mu 0 times I enclosed. We'll do this one in black. So what we want to do here is draw a big Amperian loop, which is going to go halfway through this thing. So we would have it go into this and come out the other side. And we're enclosing a certain amount of current coming out and a certain amount of current going into the page. So all the B.dl stuff aside, we got mu 0. Then we have coming out, so we'll call that positive, in times I times L. Well, this is my L on the top. So number of loops per meter times the length is going to give me how many dots out I have. Times I is going to give me that total current. That's out. Now I've got the same amount of current in. So what I have is 0 enclosed current. So that's going to tell me that outside my magnetic field is equal to 0. That's a good thing to remember. Outside of any solenoid, the magnetic field is equal to 0. That's thing one to remember. So let's go inside of our solenoid. We'll clean this up a little bit. Inside of our solenoid, we already have that Amperian loop. Inside of our solenoid, we already have that Amperian loop drawn. We're going to go from here to here, here to here, here to here, here to here. Now, we need to look at the direction of the magnetic field in this area. If I have current going into the page on the bottom, the magnetic field is going to point to the right from them, and if it's coming out of the page on the top, it's also going to point to the right. So it's good to know that the magnetic field is in this direction. We'll see about constant or not. Now, inside, we start the same way. B dot dl is equal to mu 0 times I enclosed. And we're going to get I enclosed the same way that we did before. N times L gives me the number of loops. And so that enclosed current is the number of loops I have enclosed, N times L, times I, the amount of current I have. So it's mu 0 times N times I times L. And that's equal to B dot dl. Now, for my entire closed loop, I have 4 segments of B dot dl to deal with. So I'm going to have 4 different B dot dl integrals. That's going to go 4 different ways to take care of my 4 different loops. So the first one is going to be from A to B of B dot dl. The next one is going to be from B to C of B dot dl. The next one is going to be from C to D of the magnetic field dotted with dl, and the third one is going to be, the fourth one is going to be from D to A of B dot dl, and that's equal to mu 0 times N times the current in the wire times the length that we're enclosing. Now, the cross product means that when the magnetic field is parallel to my length, it's going to give me the maximum value that we have. And when they're perpendicular, it gives me 0. And we see from this line segment, B to C, from B to C, I have 0 contribution. And from D to A, again, I have 0 contribution. And we just said over here that outside the magnetic field was equal to 0, so I have 0 contribution from that part. So it's B dot dl from A to B. Now if we stay in the same spot, our magnetic field's not going to change, so that can come out. And dl from A to B is just going to be this length, and we called it L earlier. So we've got B times the length inside of the loop, and that's equal to mu 0 times I times N times L, the length that we're enclosing. And we see that inside of this solenoid, the magnetic field is equal to mu 0 times the current times the number of loops per meter. And we see that it's constant inside of a solenoid. We won't have time to work on this, but this is how a solenoid works. We construct a square. We really only have to deal with the bottom part of the square, the length that's inside of the solenoid. And it's constant at every point. So here, here, all the way through, the value for the magnetic field is mu0 times I times the number of turns per unit length.